We are recording. Okay, so last time I went over the using a periodic stimulus. So that's obviously a special case because you have to keep doing the same thing again and again. And so that's not, obviously, there's a lot of things you can do with that. You could even do linguistic experiments or, complicated higher level things as long as you kept them periodic. So there's many possibilities. It's not as restricted as it might appear at first. But there's many times when you might want to use a more randomized design. And so that's what we're going to talk about today, which is pretty much how everybody else analyzes their data. So the general linear model, or GLM. And just to sort of put it in perspective, the thing we were talking about last time with doing the Fourier transform of the response to a periodic stimulus, that was also a linear model. So it was maybe not quite as general of a linear model. So first of all, what does it mean to be linear? So the definition of linear. So basically, the definition of linear, if you have some function, that function is linear if when you apply it to two arguments separately, it's equal to the function applied to the sum of the arguments. That's what linear means. So if so this guy is, if that's true, this guy is a linear function. And that applies, so in the simplest case, you can see, like a graph of a line, that works with a graph of a line. So if you have, A over here, then this is f of A, and you have B over here, then this is f of B. Then if you add A and B, so here's A plus B, then that number, this number over here, f of A plus B, should basically equal this one on top of that one. So obviously the linear test applies to a function of just one argument, but there could be lots of. It could be a function of multiple arguments. It can apply in a more general way. And so why do we use a general linear model when we really know it's not true? So it turns out it really isn't true for many different things. But it turns out in a very simple case of just applying a flash. So what's often done, if you have a linear system of some kind, you can characterize the linear system, you can characterize the response of the linear system to anything by just examining its response to an impulse. So if this is the stimulus, and then we have a linear system that operates on it, if that stimulus generates some kind of response like that, this would be called the impulse response function. So this is the impulse. So the impulse response function. If we characterize the system with just an impulse, it turns out we can, if it's a linear system, we can actually now say we can predict what the system is going to do to anything just from that one impulse. That's kind of why everybody wants the world to be linear, even though it's not. But you can sort of approximate it as linear in many cases. And so what we're doing when we calculate a hemodynamic response function is we're basically trying to estimate the impulse response, function. So let's do this kind of linearity test on a very simple case, and this has been done on a very simple case. And so the very simple case is do a flash. So for instance, this is a flash. and then look at the response in V1, impulse response in V1, for example, V1. So, this is the, for example, flash. So if we just do a short flash of light and then look at the response in V1, primary visual cortex, you see something like that. So then what you can do, you have to do it do the flash a bunch of times with enough time that the impulse response function dies away so that you get a nice average. If you just do it once, it's going to be messy, but average a whole bunch so you figure out what the impulse response function is. Then see if you can predict the response to two flashes that are close to each other. So if you put two flashes close to each other like that, so that's the stimulus. If it was a linear system, if it was one of these guys, then we should be able to predict what the response to this is on the basis of just the response to a single flash. And so what would you do? You would convolve that stimulus with the response. And so what would it look like? So here's our prediction. So we'll make our prediction in prediction in a different color. So here's our prediction. So basically what's going to happen, it's going to look like the impulse response function. And then when the second response hits, you should just linearly add on to it, and then the thing will die off like that. So this is the prediction. This is the prediction. And then we could actually measure what the actual response is. So the response won't be exactly like that. Maybe it's a little bit off, but the response in V1 might be something like this. So this is the actual response. Actual response to stim. And when people have done that, it looks relatively linear in V1 for a flash. So is the rest of the brain linear, or is V1 linear if you do something that's more complicated than a flash? No, it isn't. Because anytime you get any kind of habituation where if you present something once and then you present it again and there's less of a response the second time, that's not linear. So why do we do linear then? Well, two reasons. One, it's well understood. And the second reason is that the response is sort of linear. And so pretty much everybody says, well, okay, we'll just sort of we'll sweep it under the rug and just do it this way, because it's kind of easier to do it that way. And we have some evidence that V1 is sort of approximately linear. So pretty much all fMRI analysis, virtually all fMRI analysis is done using a general linear model. But it's important to sort of keep in mind that there's a limit to its applicability. Always so people are extremely worried about tiny differences in the analysis pathway of the general linear model when, in fact, the brain isn't linear. So I'm just sort of saying that to sort of just don't get so worried about the tiny differences in the analysis pathways, because the whole thing is an approximation. Okay, so that's what we're going to talk about, sort of a linear model of the brain response. And so now what we have to do is actually write this out as a linear equation, or a linear system of equations. And so there's many different ways of writing it out. I'll do a couple different ones so you get some idea of how, what the variation is. But if we write out the basic general linear model that allows for some nuisance variables, if we write it out in the most compact way, we have this experimental design matrix. I'll annotate these. The hemodynamic response function, and then plus some set of nuisance variables. That's another matrix, times a set of weights for the nuisance variables, and then plus the noise. So this is a vector equals a matrix times a vector, which gives us a vector. So a vector equals a vector plus another matrix times a vector, which gives us a vector plus another vector. So that's our general linear model. So let's actually, let's annotate it first. So this is the data. So the data, is equal to the design matrix. We'll explain what that is. Design matrix times the hemodynamic response functions. We'll start off with just one, HDR. Plus nuisance. So these are things that actually affected the response, but we're not interested in. So nuisance times weights plus noise. So that's our general linear model. So what does it look like when we draw it out as matrices? So if this is our vector of data. So here's the data. So this is data. So what are we talking? We didn't mention anything about like sort of brain images. We're just talking here about one voxel, okay? So this is all for one voxel. So we have to do the same thing for every voxel. You could average voxels together and then operate on an average voxel, but in the limit, this works. This equation is an equation for one voxel. So here's what is this? So this is basically the time of the experiment going this way. So that's the. These are all the time points of data. So this is, the first volume, the brightness of the voxel in the first image, brightness of the voxel in the second image, et cetera, et cetera. So that's the total number of time points in the experiment. So that's our data. So it's just a single row of numbers, or a single column of numbers that's for, that is one data collection. And so then that equals the experimental design matrix. And so what is the experimental design matrix? So that is basically a convolution written out as a matrix. So that's where you'll see the convolution actually sort of coming. So how do you write out a convolution as a matrix? Why would you want to do that? Well, the convolution is kind of a compact way of doing it. When you write it out as a matrix, it's kind of more of a mess. But if we just assume that the stimulus is on or off, so let's say we turned at time point 1, we turned the stimulus on. The way you write out a convolution is, so these are 1s, and so now at a later time point in the hemodynamic response function, we are allowing this stimulus to play out. So this is the way you write out a convolution as a matrix. So what does that correspond to? That corresponds to. So I just did the simplest possible design matrix, which is you turn the stimulus on and then you turn it off. So here we'll put one more set of 1s. So it's on for half the time and off for half the time. Okay, so what does that correspond to? That corresponds to here's time like that, and here's where we start, and the stimulus was on, and then the stimulus was off. So it's 1 here and 0 here. So it's, the stimulus is on, and then off. So this is all This is all off here. These are all zeros. Off, all 0. I'll only draw the ones. Okay, so that's the very simplest possible stimulus. And so it's just on and off, one voxel. Okay, so what are the dimensions of this design matrix? Well, it's got time going this way, so this is the time of the experiment. Let me just make it one wider so we have a slightly bigger hemodynamic response function. Okay, so a little bit bigger. Make one last one. Okay, this is our written out convolution. It's got, you can see that the shifting part is just from sort of going to all the z's in order to do the entire sum as a matrix. Okay, so here's that design matrix. So this guy is the X matrix. That's this guy up here. And so it's got experiment time running that way, and then this time is the hemodynamic response function time running that way. So that's how many time steps you're allowing in your hemodynamic response function. So, potentially the hemodynamic response function could be the whole experiment, but that's you're just assuming that in general, if you do something, it's going to cause some disturbance in the brain that will last, 10 seconds or something like that. So usually the hemodynamic response function is going to be, something like 10 seconds of the experiment instead of the whole, like 5 minutes of the experiment. So there's the hemodynamic response function. And then that's multiplied by a shorter vector. And this vector has to be the length of the hemodynamic response function. So here's the h vector. So this guy is h. That's our that's the time steps in our hemodynamic response function. So we'll call that the number of time steps k. And so this guy is the time of hemodynamic response function going that way. And so remember, when we do the matrix multiply, there'll be 0, 0, 0, 0, 0 like that. And so you'll multiply those numbers times those numbers, add them all up to get one number in the vector that is the output of experimental design times hemodynamic response function. So the output of this is a vector. Output equals vect. So that will give us one piece of the data that's trying to explain the vector of observations. So here's the vector of observations, and we're trying to explain that vector of observations by the design matrix which we set up, and then some hemodynamic response function. So that's the first part, and then we've got the nuisance bit. So here's the output of this is a vector. So we're adding that to this nuisance. So this guy, this is the time of the hemodynamic response function. So you can imagine the hemodynamic response function like that. So the numbers will be sort of big in the early part of the hemodynamic response function. Yeah, sorry, I'm kind of bobbling that HDR, so we'll define HDR. Yeah, so HDR equals hemo, just meaning blood, hemodynamic response function. Okay, so so here's our. Okay, so now let's do the nuisance variables. And so the nuisance variables are basically some additional things that cause a response but that we're not interested in. So so this is another matrix here, and you might have, say, like a linear ramp. A linear ramp. So, for instance, you could say, we're not interested in anything that looks like that. And what could cause that? Well, maybe the scanner warmed up a little bit and the image just kept getting slightly brighter, and so we don't care about that. So what we want to do is we say that's a real part of the signal, but we want to sort of absorb it. So here's a linear ramp, and then you might have a polynomial ramp. Polynome. So what would a polynomial be? A polynomial might be something like that. So we're also not interested in anything that looks like that over time. So we would say, like, we're not interested in anything that looks like just a ramp. We're also not interested in something that is slowly changing, goes up and comes back down, and we might not even be interested in something that does something like that. So those are nuisance variables that actually are in the signal, but we want to sort of like just discount them before we want to discount these guys so that we only get the actual response to our actual experimental design. So that's what the meaning of the nuisance variables are. There's less of them. So what you're going to have is, different factors. This is not time, so like polynomial, linear, and then in this direction, this is wrong annotation color. Okay, so these are factors, and then time of experiment is going this way. So that's the same as time of experiment going this way in the S matrix. So this is in the X matrix. So here's the S matrix, and then there's going to be a set of factors. It won't be as big as the hemodynamic response function, like that. And so those will be the weights. So this guy is the B matrix up here. It's B, and so that would be like, for example, linear weight. So that would be how strong was that linear response? Was it a big ramp or a small ramp, or was it a negative ramp, went the other way? It could be negative too. Okay, so this direction is the number of factors going that way, because we want to multiply these guys times these guys when we turn this S matrix times the B weights into a vector, which is going to be part of the explanation of the data. Okay, and then last but not least, our combination of experiment plus nuisance factors may still not explain the data. And so we have to have some sort of escape valve. And so the escape valve is here's the noise vector. And so the noise vector is whatever we need to make up the difference between the explanation that came from the nuisance factors and the explanation that came from the hemodynamic response function multiplied by our design matrix. And so this is that's the noise, and so that one is once again, this is the time of the experiment running this way. Okay, so that's our basic general linear model. Now, this is a particularly dumb experiment. It only, it's got one condition, and the one condition is on and off. So obviously that's not complicated enough for us. So the question is, how do you build in multiple conditions? So for one voxel, so here's multiple conditions. So for multiple conditions, what we need is a more complicated design matrix. So what does that look like? So here, let's take mult conditions. Now, the conditions don't have to be completely, there's no necessity for them to be completely non-overlapping because the general linear model is very general, and so you could have two conditions on at the same time. That's okay. So I'll make an illustration like that. So the X matrix could look something like the following. So if we have, I'll just draw the X matrix again. So that's the experiment time. So you could have something like this. Like we turn on a condition for a little while, and so here it is being played out over time of the hemodynamic response function. And then let's say we now have another condition, like condition B. And let's say before this one has completely died away, let's turn on, so it's still on. Let's turn on condition B at the same time, like that. So basically, for this time point, condition A and condition B is going to be on. And then, there's zero in here. And then at some later point in time, maybe we just turn on condition A again. So here's a later point in time with just condition A on. Everything else is 0, etc. An actual real design matrix is going to be a lot bigger than, bigger than this. And so then we could have, another condition, so here's another condition. Okay, so now what is that going to do to our hemodynamic response function? Well, it's going to have to be, it's going to have to sort of have hemodynamic response function 1, and then hemodynamic response function 2, and etc. So we're just going to have a column. So this guy is H1, and here's H2, because those will be multiplied by these guys. So this guy is time HDR 1 going that way, and then here's another time HDR 2 going that way, etc. So now we've got a bigger matrix, and we're solving for concatenated hemodynamic response functions for different conditions, because we don't necessarily have to have the same hemodynamic response function for all the conditions. They may actually elicit a different kind of a response. So that's our and then plus, etc. So we have you're going to have the same factors in there. Those wouldn't change. There would still just be the same number of weights, and then you would have the noise in there too. So this was just the X matrix, and this guy was the H matrix. So that's how you would do multiple conditions in X. So finally, sometimes if you read in the literature, you'll see the hemodynamic response or the experimental design matrix sort of tacked on to the nuisance factor matrix. So it's worthwhile just sort of, that's virtually the same thing, but it's a different way of looking at it. So what you could do, it's a mathematically equivalent. So you could have your data vector equals a design matrix prime that has the nuisance factors tacked into it times the hemodynamic response function, which is going to have its weights tacked into it, these b's tacked into it. And so that's sort of an alternate way of looking at it. So this gets rid of the S matrix, and then you just have that. And so what does it actually look like if we draw it out as kind of like matrices? So we've got our data vector here. Sorry, y equals, not plus. So that equals basically our X matrix. So here's the X matrix. And then all we do is we just paste on the S matrix onto the end of it. And then when we multiply by our hemodynamic response function, we've got the B tacked on to the end here. So here's the H, and then here's a B, a smaller b. So there's Y, X, and S. So we just tack on the things there. It's kind of sort of a little conceptually messier because you've got two different kinds of things here. You have a hemodynamic response function, and then you have these weights that are weighting linear ramps or slow changes. And then this is just plus the noise vector. So you might see it written out like that. It's another way you might see the general linear model written out. So that is paste X or paste S onto X. That's another way. Yet another way that's simpler is let's just assume that we know what the hemodynamic response function is. So if we know what the hemodynamic response function is, what we can do is we can just solve for the amplitude of the hemodynamic response function. And so what does that look like? So that's another way that you'll often see this written out. And so that would be, here's our data vector. And so our data vector equals the X vector. And so what is the X vector? The X vector is the vector that you get after you multiply the X matrix times the hemodynamic response function. So what is that thing? That thing is basically the X matrix times our known hemodynamic response function. So this guy, and then this guy is assumed known HDR. So if we know what the hemodynamic response function is, we can just stick it in there, and then we know what our experimental design matrix is, and we just multiply this matrix times a vector, just rotates the vector, and then we get a vector, which is essentially our predicted response. So what is this? This is the response due to experimental design. So that's our single row of numbers. It's just a single row of numbers like the data vector, the column data vector, and that it just says that that's what we can explain. And then, but that thing is going to be multiplied by a number. So that guy, which is often use beta for that. So what is that number? That's just a weight. So that's a weight. It's a single number, because remember the x is a vector. So the y is a vector over time. The x is a vector over time. and this thing is just a single number, whereas as opposed to like this hemodynamic response function is actually a vector, a set of numbers, but this guy is just a number. And so, and then if you you have the noise added onto it, the noise vector. So you might see, so what is this? This is, pre-multiply, with known HDR. So that says, let's just simplify. So now we just have a vector equation, but what is a vector equation? It's just basically a whole set of simultaneous equations. And when you look at this, now you can see it looks like, y equals, mx plus b. It looks like a linear equation. Y equals slope times x plus, intercept. It's basically just a whole set of linear equations. And so then you just solve this equation. So basically you've got everything but beta. So now you're just solving this set of simultaneous equations for beta. And so, assuming there's just one condition in this one. And so now you can sort of see that, that's really just like a linear regression. You've just got a bunch of data samples, and you're just basically you're just solving for the slope effectively. So, and then b, which is, where it intercepts the y-axis. So that's, when you boil it all the way down to this, then it looks like sort of something like a simple linear regression. But this is the general statement that we'll be talking about next time in more detail to sort of try to visualize this. So, so you might see something like this, though, as also described as a linear model. So I didn't stick any nuisance in here. We just ignored nuisance. So what you can do, another way of ignoring nuisance instead of sort of building it all in, is you could just try to subtract it out before you start. So, yet another way is, subtract out nuisance before we start. So, for instance, we just fit a line to our data, and then just subtract off that line so that we get the data down around 0. So if the data comes in, something like this, there's some linear drift in it, and then maybe you got sleepy or whatever. You just fit a line to that, subtract off that line, and then you end up with data that's just all along the 0 axis, and then you just stick that into our into our y. So basically we just subtract the linear ramp off the y, and so then we don't have to deal with the s. We'll say why that's not necessarily a good thing to do the next time, but so that's the start. So what we want to do, so let's, before we deal with this huge mess here, let's just make a little picture of how we can sort of conceptualize what we're trying to do when it comes to the point of calculating the significance. Because obviously we want to have some measure of how well does our experimental design and our solved for or assumed hemodynamic response functions explain the data. We'll just ignore the nuisance for now. How well does it explain it relative to the noise? And that's our significance, basically. So in addition to, so we solve this equation. So say we have unknown hemodynamic response functions and unknown linear weights here for our various nuisance factors. We solve for the H and the B, and then we can, given our data and experimental design, but then we have a second stage, and the second stage is how good is that explanation? And so let's start off with that one right here. So let's just imagine, for the time being, we'll forget about the nuisance, and we'll just imagine a two-dimensional space. And this two-dimensional space is basically the space of all things that we could explain. So what are the dimensions of this space? So we'll just assume we have a two-dimensional space. Okay, and so let's say in that two-dimensional space, this is our, that's basically the space of all the different time courses. So it's a space of time courses. So the dimensions of this space are actually, so a point in this space is actually a time course. So, say a point in space. That's kind of like hard to wrap your mind around. It's a time course. So it's a space of time courses that we are capable of explaining. So there's some time courses that we can't explain with our experimental data. And so let's say here's the experimental data. So this is the y vector. That's the actual data. And so now what we want to do is say, if we multiply this X matrix times our hemodynamic response function, that will basically be able to explain, so this is our X, multiplied by the hemodynamic response function, which we solved for. So we solved for the hemodynamic response function. And when we multiplied this thing we solved for times this, then we get a vector. And that vector is basically what we can explain. Now, there's going to be stuff that we can't explain, because like an example is, say, you turned the stimulus on and then you turned it off. And say the response looks something like the following. There was a big response when you turned it on, and then for whatever reason, the response went away, and then it came back for a little while, and then it went off. So clearly, you can't explain that with this experimental design. Here's our y data. It just went away there. We can't explain that part. And so that would be why this data vector lifts out of the plane of things that we can explain. And so what is what is this thing? This is the error, or the noise. Error, noise. And so basically, how do we figure out the significance? We figure out the significance just by basically comparing, this guy, this guy down here. So let's look at this guy down here. So this is the amount of the data that we can explain, which is if we project our data down back into the plane of possible time courses that we can explain. So this guy is the signal, and this guy over here is the noise. So basically what we can do is we can say, are we explaining a lot of the data relative to the noise, or a little bit of it? And that's effectively how you get your significance measure. You compare sort of this kind of signal, which is the stuff we can explain, to noise, which is the stuff we can't explain. And so this would typically be something like an F ratio, which is a ratio of variances. So a ratio of variances. But you can sort of think of the F ratio as basically signal to noise. It's just like the signal is like how much we explained, and the noise is, the part we couldn't explain, and what's the ratio between them. So how do we sort of generalize that? And so let's just say again what is sort of mention the space business. So I'll leave that up. Let me erase this guy. So one way, so where do those spaces come from? Let's just make that just as concrete as possible. So they come from the columns of the design matrix. So why the columns? So remember the stuff I'm erasing right here, the columns are the time points. E plus n, there we go. Okay, so the columns are the time points, and so when we have that matrix, like our X matrix, so that's the X matrix or the S matrix, the height of the columns is time, the time of our data. And so how do you think about these? So here's S. What you think about these is these guys are the basis vectors, like X, Y, Z. So basis vectors of X. And what are the basis vectors? The basis vectors basically define the space, and then what's a point in the space? So here's the important thing. It's a point in these spaces. So this is, basis vect of S. So point in these spaces is time course. So a single point in this multidimensional, so you could just imagine it like XYZ. So here's XYZ, and then here's a point. And so that point has a certain X, Y, and Z coordinate. And these vectors are basically the X, Y, and Z axis, but we've got, we might have a lot of them. And then what's a point? A point actually corresponds to an actual time course. So that's the conceptual picture that people have in mind here. So this space is kind of like a space of possible time courses. And that space has properties. It has here's the set of possible time courses that we can actually explain with our experiment. And our experiment is something else. I mean, the brain is not constrained by what we can explain. It can just do whatever it wants. And so here's what that did. And then what our goal is try to figure out how to find out what is the proportion of that data vector that we can explain with our experiment. And the way that you think of this mathematically is you think of these matrices, experimental design matrices, as having basis vectors that are defined by the actual columns in that matrix. So that's the that's the start. So it's looking bleak now, I admit, but what we're going to try to do next time is draw out for the general case, this general case here, how do you actually, what's a geometric picture like this one, a little more complicated, that will show how we actually calculate the significance of a response. So that's the plan for next time. And what I'm going to go over, if you want to look over it in advance, Tom Liu et al. Wrote this from UCSD, wrote this very nice paper, which is in the readings in 2001. And the later parts of the paper are harder to read, but the first 2 or 3 pages of the paper are good. So go to the first 2 or 3 pages of that paper there. It's very clearly written, and I'll go over that. I'll go over the sort of the main points of that that paper next time to try to get a geometrical idea of, how the nuisance factors can get us in trouble, because the nuisance factors might not be orthogonal to the experimental design matrix space. So these vectors might not be orthogonal to these guys. So I think, David, I'll stop there and ask for some questions.